These regularity results for parabolic stochastic PDEs.
Thank you very much. And thank you very much for the invitation and to include me in your workshop here. You see already my topic, regularity results for parabolic stochastic differential equations. But let me say right away I will focus on maximal regularity results. So let me start from a model equation. I just look at the Laplace operator. It's a linear equation. I have beta of t as a scalar Brownian motion on an appropriate filtered probability space. I have that G takes its values in an LP space with p larger than 2. And then it is a process. It's adapted, and with respect to time and probability, it's in an LP space. And then I can ask for the solutions of this linear equation here. And I can ask in particular for the maximal regularity solutions. Well, it's well known now, by the way, from the work of Grylov, that this equation here, the maximal regularity for the solution, will be, it has one derivative. It will take its values in W1p, and moreover we have such a maximal linearity estimate. That means if we take this first derivative, then we can estimate the solution in the same space, in the same LQ space as we measure the right hand side. And such an equation within a space LQ is very useful if one looks at nonlinear equations, because such an estimate will allow for fixed point arguments that allow you to solve the nonlinear equations. So this is just a simple linear equation. Of course, our goal is to look at more general equations. Eventually we want to replace the scalar Brownian motion by a Wiener process. We want to replace the Laplace operator by systems of elliptic equations, and we also want to add nonlinear terms in the deterministic and in the probabilistic part. But before doing that, it's still useful to understand this linear equation a little bit better. And for that, let us discuss how this equation comes about. So you can have the weak solution given in terms as a mild solution in terms of the stochastic integral I have written here in black, and then we add on both sides the derivatives. So maximal regularity means that this stochastic convolution operator is bounded in these spaces here. So here I have the maximal regularity inequality again, and I would like to rewrite it as boundedness condition for the stochastic convolution. For that, I use the Ito isomorphism in the space LP. This means the stochastic integral in the LP space can be estimated by such a square function expression here. So you see again, the h of s is a function with values in the function space LP. And so I can evaluate at points in Rn, form the square function, and take then LP. So if P equals 2, I get the usual Ito isomorphism in L2. In LP, I have to use such a square function. Now, if I just translate the estimate of, the LP norm of this stochastic convolution here, then I end up with an expression of the following kind. I have the square function of the stochastic integral, and then I take the LP norm, and I take the time norm, and I take the expectation. So this is just another form of this equation here. Now, in order to get familiar with this last expression here a little bit, let me first make a little calculation. And I am a little bit less ambitious now. I replace the first derivatives by less regularity. I take a fractional power of the Laplacian with alpha strictly smaller than 1/2. That means I have less than one derivative in regularity. Well, and in this case, I can do a simple estimate. I use Minkowski's inequality to pull the squares out and have the norm inside. If I look now separately at the norm of this operator, of course, e to the minus ts gamma is the Gaussian semigroup with this fractional Laplacian in front of it. Now, it's well known how the norms of these operators are estimated. In this case, the norm would be the difference t minus s to minus alpha and then squared. So, since my alpha is strictly smaller than 1/2, I have here now an integrable kernel, and I can estimate this convolution operator in the space LQ over 2. And then I just get my right-hand side and the L1 norm of this kernel here. So that's an easy estimate. But you see, it gets more difficult as alpha approaches 1/2. Yeah? If alpha approaches 1/2, then we are approaching here a singular integral, 1 over t minus s. And so we have to expect some trouble in the borderline case, which represents maximal regularity. This also is seen in a different way. Krylov has called this inequality the generalized Paley-Littlewood estimate. And the reason is, if you choose special functions which are, let's say, 0 on the first part of the interval and then constant some value x on the second part of the interval, you can see that this generalized or more complicated Paley-Littlewood inequality reduces to the classical one. Yeah? You look here at the Gaussian semigroup times the gradient, and you take a square sum of it in the LP norm. And now this is a non-trivial inequality from harmonic analysis, that this kind of expression can be estimated by x in LP. And so what we see here is that the maximal regularity we are looking for, the case alpha equals 1/2, that this is actually harder than the classical Paley-Littlewood theory, and one would expect that one needs some non-trivial harmonic analysis to prove something like this. And this is actually what Krylov did, and this inequality is the first major step in his LP theory of stochastic partial differential equation for the Laplace operator, so to say. Well, from there he goes on to non-constant PDEs, and he uses very delicate stochastic arguments to include nonlinear terms, and then he uses PDE methods to go to coefficients which are space dependent. But this is the first non-trivial step in the whole program, and a lot of inequalities are in the end reduced to this one. This is the starting point from which you generalize. Now, instead of going into this, I would like to talk shortly about a second approach to the same problem. Let's first go to the Hilbert space situation. Of course, Hilbert's space situation is simpler. Also, the result on the Laplacian was known much longer in that case. And actually, in Hilbert space, there is a result from D'Abrato from '83, which looks at the same linear equation that we just looked. He just replaces the Laplace operator with the generator of an analytic semigroup. Yeah, everything else is the same. We have here a right-hand side which takes values in a Hilbert space, and then we want an L2 estimate with respect to time and probability. Now, in Hilbert space, usually with Gaussian processes, everything works fine. I mean, the norm, independence, everything is just fitting too well. But even in Hilbert space, you cannot prove this maximal regularity result for any analytic semigroup. The additional additions that assumptions that D'Abrato made were, on the one hand, that the domain of a to the 1/2 equals the real interpolation space. That's one possibility. And another possibility was that he assumed the semigroup is contractive. So both possibilities are enough to get the maximal regularity inequality. And one can say a little bit what is behind that. You see the two conditions, the contractivity or the interpolation assumption on the domain, they both imply that we have, well, you could say that we have such a Paley-Littlewood inequality for the operator A again. I mean, now we just take everything L2, but we have a to the 1/2 times the semigroup applied to x, and then the square integral gives a new norm equivalent to the original norm. And if you have this, let's call it Paley-Littlewood inequality, then it's not hard anymore to prove the generalized Paley-Littlewood inequality, which is the same as the maximal regularity inequality. I wrote the couple of steps out for you. I mean, here we start with the translation of our maximal regularity inequality in terms of the stochastic convolution and ethos isomorphism. And then everything is 2, so we can use Fubini twice. And we end up without any estimates at this integral here. Now you see the inner integral is precisely of the type of our Paley-Littlewood estimate, and so we can directly estimate the inner integral in terms of the norm of g of s, and we get our result. So this is the Hilbert space situation. And motivated, I think, by these examples, Bresniak made a theory for for spaces with martingale type 2. In this talk, I would like to stay in the framework of LP spaces. So let us assume that E is a closed subspace of a space L2, which has now any measure space. Measure space does not have to be structured. And we assume again that A generates an analytic semigroup, and then there is an assumption which you could call spectral theoretic assumption. He assumes that the imaginary powers of a to the t are bounded. Well, for comparison, let us look again at our basic linear equation, just as in the Hilbert space case and for the Laplacian in the beginning. Then what Bresniak shows is he has maximal regularity results in a scale of Banach spaces that he constructs from the given one. Basically, they are in the scale of real interpolation spaces between the domain of A and an extension, the so-called extrapolation space, given the operator A. Now, to be more concrete, the scale that he constructs would be precisely the Bezoff scale in case of the Laplace operator. And the big advantage of his approach is that he can deal with norms which have, again, this Paley-Littlewood structure. This comes out of the way these real interpolation norms are defined. This allows you to get norms which are equivalent to such square integrals, to such Paley-Littlewood functions. And then you can do similar things as in the Hilbert space case if you have that. And with his method, he is successful in dealing with certain boundary value systems, which is a particular difficulty for this maximal regularity results. There is one disadvantage to his approach. The scale that he constructs is basically always different from the scale of fractional powers, which would be, again, for the Laplacian, the classical Sobolev spaces. So the difference is between the Bezoff scale and the classical Sobolev spaces. So these are some of the known results. And now one can ask the question, on the one hand, we have the very precise results of Krylov in LP for elliptic operators, and the precision is based on the very good estimates from harmonic analysis. On the other hand, we have the results of Dabradin and Bresniak, which have a certain generality because it's in the framework of analytic semigroups, which really covers lots and lots of important situations. And the question is, can we somehow combine these two features? And I would like to present you now a result which goes in this direction. So this is joint work with Jan van Nerven and Marc Verrat, who is here. And we also look at the situation where A is a closed subspace of a some measure space LP. So this could be a Sobolev space, this could be a LP space on manifolds, this could be a LP space on an infinite dimensional probability space. And then our essential assumption is that the operator has a H infinity calculus. Let me say a little bit later what that actually is. For now, I would like to point out, if we look at our basic linear equation, the same as before, then under these assumptions we can prove the existence of weak solutions which take their values in a to the 1/2. Yeah? So if A would be the Laplace operator, a to the 1/2 would be the first Sobolev space. So it's half of the regularity of the whole operator A. If we look at a Cahn-Hilliard equation where we have Laplace squared, then this here could be two derivatives, a to the 1/2, for example. Okay, we have values with this regularity, and almost more importantly, we have again the maximal regularity estimate, which is an estimate in a fixed space of processes, which will be important to do fixed point arguments for nonlinear equations. Of course, if we have this maximal regularity estimate, then we also have the generalized Paley-Littlewood inequality I was talking about. They are more or less equivalent. And now I can close the circle a little bit of what I was talking about. One way to define a H-infinity calculus, although that would be an awkward definition, we will look at a better one later on. But one way would be to say the norm in the space E is equivalent to this square function estimate, which is again a Paley-Littlewood estimate, but now custom made for the operator A. Yeah? If I choose A as Laplace, then I get the classical Paley-Littlewood estimate from harmonic analysis. So in one way, what we are saying is that if you have the classical Paley-Littlewood estimate, you get the generalized Paley-Littlewood estimate, which means you get a maximal regularity estimate. Well, let me just say that behind this result there is a long history. Of course, there is Paley and Littlewood with their work, and then McIntosh, Yagi, Cowling, Dowse, Lemerty, and Colden and myself, we generalized this work in an ongoing process to the kind of situation you have now before you. Let me give you a little bit more information that comes out of our work. We can trade, we have so far we had maximal space regularity, and now I would like to point out we can trade some of this space regularity away to get a corresponding amount of time regularity. So if I'm willing to give up order alpha in the space regularity, I can win the same order in time regularity. I mean, these kind of techniques, they are already done in Bresniak's work that I mentioned earlier. And the second information that comes out of it is that one has maximal estimates. Not only in the space E, but even in a smaller space in between the domain and E. Well, the technique gives precisely this kind of interpolation space, but in particular the maximal estimate does also hold in E, and so we see that we get nice continuous processes in E, not in dA to the 1/2. I mean, there we get processes that are usually not continuous. Well, and then one can ask, how special is this assumption of H-infinity calculus? It does not characterize the maximal regularity estimate, but it comes close in a sense. First of all, it comes close in the sense that the examples which exist and show you the difference, they are very artificial. You're not likely to see them in any applications. So I would dare to say, for all practical purposes, this H-infinity calculus and maximal regularity are the same. And this can be made more precise in the Hilbert space setting. There you have that your operator has such a H-infinity calculus if and only if A and its adjoint has the maximal regularity estimate. The thing is just that the H-infinity calculus is a two-sided estimate, yeah? And the maximal regularity estimate is one-sided. This is why I had to include the dual here. Well, to make this a little bit more concrete, let me first mention some examples for operators with an H-infinity calculus. In Hilbert space, it's known in the meantime that A has an H-infinity calculus, well, if and only if this condition of D'Abrado is fulfilled. Yeah? If and only if the domain of A to the 1/2 can be obtained as a interpolation space, as a real interpolation space. If and only if this is not quite true, if there are contractions in an equivalent norm. Yes. Let me see. Well, then I just have to say it with emphasis again. This is true in one direction. In the other direction, if you have an H-infinity calculus, then you get a contraction in an equivalent Hilbert space norm. Okay. And it's also equivalent to have this Paley-Littlewood estimate. And by the way, this is the equivalent norm that one can use, yeah? About which I'm speaking here in the first point. Then, if we go to LP spaces, there's a general result which says if A generalizes or generates an analytic semigroup bounded on some sector, positive and contractive on the real axis, then it automatically has the H-infinity calculus we need. And that would be a general result that covers a lot of operators that naturally appear in stochastics. And then, of course, there are more analytic results. You have systems of elliptic operators, also of higher orders, on domains with boundary conditions. You have Schrödinger operators, you have Stokes operators. There is a large literature which tells you that such an H-infinity calculus exists and which can be used through our result to get automatically the stochastic maximum regularity result. So from such a deterministic result, you get automatically the stochastic result then. I will say a little bit more about the last point later on if I have time. Of course, for an audience of people working in stochastics, the question must be, why would you use such a functional calculus, yeah, in stochastic PDEs? And I would like to answer this question a little bit more in detail. I mean, I gave already one theoretical answer. The H-infinity calculus is just equivalent to this Paley-Littlewood estimate that we need. But now let me try to present a second argument. So the point is that we want to show the stochastic convolution is a bounded operator on our maximum regularity space. Now let's start real slow and take a very simple operator. Let's just take the multiplication with lambda as an operator. Real modest example. And for this example, the stochastic convolution is then simply a convolution with such a scalar kernel here. And for such a scalar kernel with exponential functions, we can make our estimate easily. You know, we need to go back to this generalized Paley-Littlewood estimate, which expresses the boundedness of our stochastic convolution. And since these things are scalar, we can just take Minkowski's inequality again to pull the squares inside and have the LP only in this place left. And then we recognize that the convolution inside is just a convolution operator in the space LPQ over 2. Yeah? And Q was larger than 2. So we can estimate this by the L1 norm of this kernel here. It's just a classical convolution. So we get that our simple example is bounded. And now, if you like the functional calculus, you could say, aha, all I have to do is to plug in. Yeah? In functional calculus, you plug the operator in a function and you are done. And this is the idea that we would like to realize now. Yeah? Of course, that's kind of a vague idea. Can I just plug A into this function and get the full convolution? How can I do this? How can I justify this? So I need a good way to plug operators into functions. And this is precisely what the H-infinity calculus does. So in our education in graduate school, we look at the Dunford calculus, which is the Cauchy formula, and we plug in A here and into the resolvent to get a functional calculus. Now, of course, we are looking at partial differential operators. We are looking at unbounded operators, so they have an unbounded spectrum in some sector, usually. So our Dunford integral will not be taken over a closed path. It will be taken over the boundary of such a sector here. And now the usual parabolic estimate is that the resolvent on such a ray decays like 1 over lambda. So here we have now an integral over the boundary of the sector with a bounded analytic function and a function that decays like 1 over lambda. So it doesn't quite converge. So in a way, what the H-infinity calculus is, the bounded H-infinity calculus, it says all these integrals converge anyway, in spite of the 1 over lambda. In other words, you're forcing lots and lots of singular integrals to exist, and that's the connection with harmonic analysis in the end. So formally, you can put in here just special values of x for which the resolvent has a better decay, and you know, okay, for such special x the integral exists. Then you need a uniform estimate, and if you have that, hopefully with an approximation procedure, you can construct a bounded algebra homomorphism from the bounded analytic functions into the bounded functions. Or put another way, you force this singular integral to exist for all kinds of f's. I mean, one example of f would be f of lambda equals e to the lambda I to the t lambda, and if you plug a into that, you get the bounded imaginary kernels. Okay, this is not what I wanted. Sorry about this. This is the function I wanted. And
Question, what is H infinity?
H infinity stands for the bounded analytic functions on such a sector here. And I want to have a calculus for these bounded analytic functions. And that's an assumption on the operator, to force the operator to have that. That's not a trivial assumption, because if you look at this example here, lambda I to the t, so these are not, they are very oscillating bounded functions. Yeah, this is not clear that this integral here is bounded, but that's what I'm assuming here. I can have also these functions here bounded, and here you see another connection with Bresniak's work. He assumes the boundedness of these, so his assumption is also close to the assumption of the H-infinity calculus. Okay, now if you allow for the possibility that I can put A into such a bounded analytic function, I get very confident and say, okay, let's do the same thing also for operator valued functions, not just for scalar analytic functions. And the background, of course, is, you see, a moment ago we were constructing for each lambda such a stochastic convolution with a scalar kernel, but it's an operator. However, as a function in lambda, it's analytic and bounded. It just has its values in operators. So that's what I'm saying here. Yeah? I think of the family of kernels as an operator-valued analytic function. And now, let's just be optimistic and say, okay, we can plug A into this function. What would we get? So I assume that there is some bounded operator, so that the Dunford integral with the scalar functions f lambda replaced by the operator valued function k lambda makes sense. Yeah? That's what I mean by plug in. There is a bounded operator which agrees with the Dunford integral for special values here that make sure that the integral exists. Now, if I'm willing to assume this, then the result becomes a formality, because, okay, here is my Dunford integral for the family k lambda. Now I plug in the definition of the k lambdas. This is my stochastic integral. And now I use stochastic Fubini theorem in order to pull out the stochastic integral. And what I have inside is now again a Dunford integral, but for these scalar functions. And these scalar functions, they precisely give me a to the 1/2 e to the minus t minus s a. So I know that such a formal operator here that exists out of my calculus agrees with the stochastic convolution that I'm looking for. And the whole question is now reduced to the question, is this realistic? I mean, if I look at a bunch of Dunford integrals here for special enough functions, do they agree with a bounded operator? And this question one can answer in the affirmative using a result from spectral theory by Corden and myself. We have a bounded H-infinity calculus, just anything. And now we look at the bounded analytic functions, but with values in the operators, not in the scalars. And the question is, what do we need in addition to make sense, well, to get a bounded operator by the Dunford integral? And there are two conditions. One is that the operator values, they commute with A. They commute with the resolvent of A. And the second condition is these also the set of values cannot be just bounded. It has to have a stronger boundedness property, which I will say a little bit in a moment. But first of all, I would like to point out that the stochastic convolutions, you see, the A operates on the space and the convolution operates on time, so they commute. That's easy, that's no problem. So the question is, will the second condition be satisfied? Let me first say what the second condition means. So by gamma bounded, I mean the following. You take elements finitely many out of the set of operators tau. You take finitely many vectors x out of E, and then you form a random sum. You look at the Tj, xj, Gaussian random sum. The gamma j's are normalized independent Gaussian random variables. And then I look at the second sum where the Tj's are missing. And what I want is that the Tj's disappear in this estimate. So if the Tj's were scalars, that would be just Kahan's contraction principle. But for operators, that's not clear if they disappear. It's an assumption. There are other ways to look at this assumption, which show that this assumption is not foreign to stochastic analysis. If you look at the stochastic integral, you have a family of operators applied to a function with values in E. You take the stochastic integral, and you can imagine there are many situations where you would like to get rid of the Ts and just estimate this by the stochastic integral of the Gs. Now this is true, this happens if and only if Ts takes their values in a R-bounded set. Or if you prefer the harmonic analysis point of view, if we are in an LP space, then a classical result of Sigmund tells us that these random sums are equivalent to the square functions. And then you get here a square sum, Tj, xj, and again the condition is that you can lose the Tj's, and actually this is a condition. It doesn't have a name in harmonic analysis, but it occurs all the time in connection with Paley-Littlewood theory. So I have a little bit more time to give you a rather quick outlook what one can do with such a maximal regularity result than for nonlinear PDEs. So I'm still in the situation that E is a subspace, a closed subspace of LP. And then I look at an equation where A of t is a family of analytic semigroups depending on time, but having a uniform H-infinity calculus. But then I add a nonlinear deterministic term f. The solution depends on it. And I have here a family, an independent family of Brownian motions. So the last term here presents a cylindrical Wiener process. And the coefficients Bj's here I just chose now as linear operators. But so they are dependent on the solution, but in a linear term. So the x of t is missing here. And now, what does this have to do with maximal regularity? It has to do with the strength of the nonlinearities. You see, for example, I can allow that the nonlinear term f is defined on the domain of on the common domain of these A of t's. So in case that we have a Laplace operator, that means f is allowed to depend on second derivatives. And the b's, well, they are linear operators from the domain in a to the 1/2. That's a little bit formal. I mean, most of the time this would be just powers of the solution or functions of the solution. And then we need to have that these random sums can be estimated in terms of x. The last condition has something to do to make sure that this sum here can be interpreted as a stochastic, as a cylindrical Wiener process. But again, the jump in here is from domain to the 1/2. So that means if it would be the Laplace operator, I can jump here by a whole derivative, yeah? Not just a fractional derivative. And then the result would be that our equation has a solution. You can interpret it as a strong solution because it takes its values in the domain. It belongs to the maximum regularity space, and it has also some smoothness property. So these are the kind of solutions one can get. And since this was very abstract, let me just show you some concrete situations we have in mind. So if we are in Rn, we may look at elliptic systems which are elliptic, parametric, elliptic. And then it depends what we need to get our H-infinity calculus. The classical results have some Hölder continuity on the leading coefficients. But there are other results which can do even with VMO conditions. And then the setup is as follows. We are looking at the space LQ, Q larger than 2. The domain is then, in this case, the Sobolev space of order 2 or of order 2m. If I have elliptic operators of higher order, then the a to the 1/2 would be the usual Sobolev space. And the point of the exercise is that the nonlinearity, the deterministic nonlinearity, can depend on the derivative and the second derivative, and the term for the the stochastic nonlinearity can make a jump of one derivative. Okay, there are also divergence form operators, and you see the point is that I use results by Amann-Hieber, Simonet, Song, and many others that give me the H-infinity calculus of these operators. And what is also some progress, I think, is that you get rather general results for boundary value conditions. Yeah? So we have some domain in Rn, and all we need is that we are in a setup where our operator and its boundary values generate an H-infinity calculus. Yeah? Then we can plug this in our theorem and get results for nonlinear stochastic PDEs. Thank you.
Any questions? In your nonlinear term, the continuity of f with respect to the highest derivative, we assume that the coefficient is small or what?
Yes, I did.
That's okay.
That was. I mean, there are Lipschitz constants, and what I need is they are sufficiently small, and how small they are is determined so far by the size of this H-infinity calculus.
And can you allow this operators to depend on omega and t and omega?
Yeah.
So t in T is continuous and say predictable.
Yeah.
But then uniform continuity in time, uniformly in omega.
Yeah.
So no measurable coefficients in time.
Only to the degree that we have continuity of the ATs as operators from the domain into X, for example, as our dependency in T at this point.
I wonder what part of your result survives if you introduce nonlinearity in your equation in slightly different form, in the form Laplace of phi of x, where phi is close to leading function to this or that sense. What part of theory will survive?
So if I understand you right,
Okay.
you first have the derivative and then you have
Laplace of
Yeah.
phi of x. And phi is close to leading function in any sense you like.
So, well, I mean, the crucial thing is the ellipsis.
Okay, fine.
And
What theory will be still true, and what kind of conditional phi you need to run your...
okay, I need, can you tell me again the
Okay,
linearity you want?
d x of